Our project is on the topic online budgeted matchings with advanced applications. We have performed a survey into methods and techniques for online bipartite matching. Multiple variants have been defined and have been studied extensively. These find applications in tasks such as assigning jobs to servers and modeling auctions such as the AdWords auction. The input for this problem is a bipartite graph G with partitions L and R and an edge set E going across the partitions. The vertices in R arrive online in a predetermined fashion, and as each vertex arrives, its neighbors in the set L are revealed. A matching M is output. We would like this to be the maximum matching, but since the input is given adversarially, we instead analyze the competitive ratio and see how close we can get to the maximum matching. This was first studied in 1990 by Karp, Vazirani, and Vazirani. Further generalizations such as B matchings and budgeted matchings were made. Random input models instead of the worst case input model were also studied. The first algorithm that was implemented or proposed was the ranking algorithm. This is an easy to state randomized algorithm which has two phases. First is the initialization phase, in which the vertices in L are assigned ranks at random. Then comes the matching phase, where each arriving vertex of R is matched to its highest ranked neighbor in L. This gets a computative ratio of 1 minus 1 over which is shown to be optimal. The proof sketch for the computative ratio is as follows. The dual problem is established by showing an equivalence between L and R, which are both ordered after the initialization phase. So it does not matter if the vertices of L come online or if the vertices of R arrive online. Refusal algorithms are defined, which either match the incoming vertex to the highest ranked vertex or refuse to do so at all. An example of this is the early algorithm, which matches the ith vertex to the ith vertex of the other set. It matches the ith vertex only if the ith vertex of the other set has not yet been matched. The worst case input distribution is found out to be the set of upper triangular incidence matrices, and analysis of the early algorithm is performed. Ranking algorithm performs better than the refusal algorithm, so this would prove as an upper as a bound for the competitive ratio as well. However, in 2008, Goel and Mehta found that this algorithm was incorrect and proposed an alternate proof of the correct result, which is that the competitive ratio is 1 minus 1 over E. Optimality is shown as follows using the random algorithm, which matches incoming vertices at random. The input distribution chosen is the complete upper triangular matrix, and it is shown that the random algorithm performs equivalent to a deterministic greedy algorithm in this distribution, which creates a matching of size n times 1 minus 1 over e. The proof is then complete by Yavan's min-match principle. Are deterministic algorithms any good? No, we show that competitive ratio of any deterministic algorithm may be at most half. Suppose an algorithm is able to match its first n by 2 vertices. Then the others can be made impossible to match by the adversary, which will now only create edges to the vertices that have already been matched. What if we give vertices in L some budget by allowing it to be reused? This leads us to B matchings, which was studied in 2000 by Kalyana Sundaram and Bruce. They produced a deterministic algorithm and showed that it is optimal. The partitions are denoted S and R, denoting sites and requests. An algorithm may match a site at most A times, whereas the adversary may match it B times. We have come closer to budgeted matchings and the target of modeling auctions by allowing a small budget, even though bids are now only 0 or 1. Balance is a simple greedy algorithm which matches requests to sites that have matched the least number of requests so far. An adversary is defined and the analysis is done over A plus 1 phases. As you may expect in each phase, the number of permissible sites to which edges are given to the requests keep shrinking. So in the last phase, the algorithm will not be able to perform any matching at all. And this produces a competitive ratio as follows: 1 minus 1 over 1 plus 1 by b to the a. This tends to 1 minus 1 over a when a equal to b and b tends to infinity. And when a is equal to b and both are 1, then we recover the online bipartite matching problem, and the competitive ratio turns out to be half as shown before. This competitive ratio is shown to be optimal, making balance the optimal deterministic algorithm for this problem.
We now look at the adverse allocation problem and generalized online matchings. The adverse assignment problem is as follows. We have n advertisers, with advertiser I having a budget of Pi. We have Q queries that arrive online. Advertiser I bids CIQ for query Q, and we need to devise an allocation mechanism that maximizes revenue while respecting budget constraints. We can see that the B matching problem seen earlier is a special case of adverts, with all bids being binary and budgets being equal for all bidders. MSVV05 views adverts with small bids, adverts problems where bids are much smaller compared to the budgets, as a generalization of online bipartite matching. In the B matching case, the only criterion to rank different bidders was the amount of budget they have left without spending. But here we also have the bids of different bidders. So a trade-off between these two values needs to be achieved. And to that end, a trade-off function psi of x equal to 1 minus e power x minus 1 is defined by MSVV05. And the algorithm is as follows. Allocate query Q to the bidder with the highest bid price times psi of fraction of budget spent so far. So if a higher budget is spent by that bidder, then their psi is lesser and their weighted bid is lesser in some sense. One can also note that if the bids by all bidders are the same, then this algorithm is just a case of the balance algorithm. Psi is found by analyzing the linear problem of the small adverts problem. And this algorithm is said to have a competitive ratio of 1 minus 1 by e. So the proof goes as follows. The budget space of the bidders is discretized into case labs. And we first start by analyzing the B matching problem. We do this by solving a linear program with variables as xi for each of the bidders. And xi is the number of sites or bidders that exhaust I slabs or are matched I times. And the primal and dual of this LP is analyzed, and a solution is found by setting all constraints to equality. Now, we also construct a family of linear programs for the small adverts problem. And we have a family here because we consider different trade-off functions psi. And we note that the dual constraints for both the B matching linear program and adverts linear program is the same. The objective function is different though, but we can set the constraints to equality to obtain the optimal for these classes of linear programs. And because of that, the dual solution for both the problems ends up being the same. And from this, we get psi to be the mentioned value. And the comparative ratio tends to 1 minus 1 by e as the discretization becomes final. We also get limits of randomization in this paper, like how we saw limits of determinism for the B matching case. The paper also shows that no randomized online algorithm can have a comparative ratio of better than 1 minus 1 by e. And the worst case input that it considers is the bid matrix being a lower triangular matrix with the rows as bidders and the columns as the queries that come in rounds. So for round I, we have B identical queries, and the query structure is as follows. In the round I, the bidders 0 to I minus 1. So bidders 1 to I minus 1 send a bid of 0, while bidders I to n send a bid of 1. And opt is basically matching all queries of round I to advertiser I, having a total revenue of n times B. However, deterministic algorithms have an expected matching size of opt times 1 minus 1 by E. With Yau's minimax principle, we get the limit for randomization. One source of discomfort in the previous analysis, or in general worst case analysis, is that such worst case input models occur very rarely in reality, and hence looking at realistic input models and providing some sense of expected case analysis would be a better metric to judge different algorithms. And to that end, adverbs with realistic input models came into picture. Two input models are studied. One is where the queries are randomly permitted, and the other is where queries are independently sampled from identical distribution. We go back to the natural algorithm of 3D, where when we get multiple bids, we choose the highest bidder and allot the query to them, irrespective of their budget. And we want to see how they perform in these models. And it's shown by GM08 that there's a 1 minus 1 by comparative ratio. We also get a simpler proof to ranking using a duality principle between ranking and 3D. And since ranking's proof had an error, this provides a simple proof to ranking. We now first look at 3D in the online bipartite matching case, and we look at points of difference between both the algorithms. Let us consider the known set as the girls and the set arriving online as the boys. 3 points of difference are misses, where boys go unmatched, good matches, a girl being matched after her optimal match arrives, and a bad match being a girl being matched before her optimal match arrives. In a good match, a girl and her optimal match are guaranteed to be matched, but in a bad match, that's not the case. We show that each miss leads to more good and bad matches. So, three properties of 3D are crucial to arriving at the 1 minus 1 by comparative ratio. The first is the prefix property. Two permutations of boys with the same prefix have the same greedy matching for that prefix. Monotonicity. If a boy is moved from some position up front to a position t, then girls who are matched by time t get matched by time t plus 1 in the new permutation. And the third is partition. If we remove a girl's optimal partner and run the algorithm, let us say a girl gets matched to a boy at position t. If the optimal partner is added back to the permutation, whether P has a good match or not depends only on her optimal partner's position relative to T. These three properties are crucial in establishing the bound, and these properties also extend to the small adverbs problem and help given linear program to get this ratio. The problem of what is the optimal algorithm for these two distributional models was left as an open question by this paper.
I will be discussing two papers, starting with the beating 1 minus 1 by A comparative ratio. So this paper introduces a randomized algorithm for the stochastic bipartite matching, where impressions occur at some known distribution. We get a type bound of 0.67 in this algorithm. We start off with seeing the greedy suggestion algorithm, and then we improve it further. So starting with the greedy algorithm, we use offline matches, which is built on the expected graph to get the online matching. We do this by solving a max flow problem by adding a source and sink. The source is connected to all the advertisers with the capacity 1. The sink is connected to all the impressions with the capacity E of I, being which is the expected number of times the impression I occurs in the online matching. And the flow of an edge belonging to E is either 0 or 1. After solving the integral model, we we can use this matching online where if an impression I dash of type I occurs, we can choose the advertiser A dash with the probability of F A dash I by E of I for all the A dash is connected to I in M of. We extend this two-suggested matching algorithm by using the Maxwell problem on boosted capacities. The source advertiser being capacity 2, edges being capacity 1, edge impression to sync being capacity 2. So we have the set of edges which belong to E but have a non-zero flow, and we color the cycles and the paths in a given manner. So for all the cycle edges, we color them blue and red alternatingly in any given order. For all the odd length paths, we color them alternatively blue and red with more blue than red. For the even length paths, for all the even length starting with node from advertisers, we alternate them from blue and red. And for all the ones starting from the nodes in the impressions, we color them first two blues, then alternately red and blue. So for any given, after the coloring is done, we use this offline matching to guide online matching and given manner that in the online matching, when impression I occurs, we first match it using the blue edge, then match it using the red edge. And for this given algorithm, we get a comparative bound of approximately 0.67, which is greater than 1 minus 1 by E. For the budget WS algorithm, here we provide algorithm for small adverts bipartite matching. First, we saw the single valued adverts problem. Then we extended to the small adverts problem with the given assumption. For the single valued algorithm, we first denote what PJ is, which is a random value chosen from 1 by E to 1 for every bidder, a revenue RJ for each bidder, and utility UI initializes 0, and the maximum number of queries as KJ for each bidder. We have a value called E bit of J being the effective bid for each bidder. So when a query comes up, we look at all the possible available bidder options which have not maxed out their queries yet, and the largest effective bidder is chosen. Utility after creating the matching utility of I, the impression will increase by is equal to E bit J, and revenue increases by BJ into BJ. As you can see, the total increase is equal to the revenue of the added bid. We introduce a new thing called J star, which for an individual bidder, which has all the possible impressions which are linked in the initial graph, and the expected value of J star would be the expected value of the revenue of the bidder J at the end of the algorithm, plus the summation of all the utilities of all the possible impressions. So given here, we find the expert value weight, which turns out to be summation of J star for all the given bidders, which we find to be greater than or equal to summation of Kj into Bj for all the given bidders into 1 minus 1 by E. Summation of Kj into Bj gives you the maximum possible weight for the entire problem. So we can, from this we get the computer ratio of 1 minus 1 by E. If we extend this to the normal AdWords case with in almost similar manner with a few changes where LJ denotes the current budget of the given bidder along the during the algorithm. Another value called WF, which calculates the false money. False money occurs when there is a bid which has a higher value than the budget given for the advertiser, and when the matching is made, the false money is added up in by bid maximum of 0 comma bid I comma j minus lj, and the remaining algorithm remains the same given the same computer ratio. The reason we take small is because we try to bound the value of false money with the given constraint. So for small adults case, we have the constraint where u of I, which is given as this, tends to 0 as number of instances become infinity. We can also bound the false money as the given value where bid of I comma j minus 1, 1 being in place of lj. So we can from these two equations we can see that mu of I will always be greater than or equal to weight of f by total weight of the w of p. And as I tends to infinity, we can say that wf by weight of p also tends to 0 as it's lesser than mu of I, limiting the amount of false money, which allows us to do the small adverts case. Now we look at a few open questions given on the Papa papers. So we don't have the best algorithm for the given models where we don't have a permutation model which has a common algorithm 1 minus epsilon for any adverts problem. And for the IID model, which is the stochastic model, we have a few proposed algorithms, but we still haven't found what the optimal algorithm is. For the adverts, all the papers we have discussed so far only deal with small bits, but do not give a solution for the large bits. For the IID solving where we beat 1 minus 1 by E bound, we have the algorithm which only takes choice of blue and red in giving only two possibilities, but we can extend the algorithm to have multiple choices instead. Thank you.